These are two numbers, 67.4 and 73.0. They are not dramatic numbers. They are not large. They are not memorable. If you saw them written down with no explanation, you would not look twice, and that would be a mistake. Because beneath the ordinariness of these digits, beneath their apparent smallness, is something that should not exist, a crack in our understanding of the universe itself. These two numbers are both measurements of the same thing, the Hubble constant, the rate at which the universe is expanding. How fast space itself is stretching, carrying every galaxy away from every other galaxy. There is only one universe. It is expanding at one rate, so there should be only one answer. There are two completely independent methods. No shared instruments, no shared assumptions. If these measurements had been made 50 years ago, when the uncertainties were large, two different numbers would have been expected. The error bars would have overlapped comfortably. The disagreement would have dissolved the way morning fog burns off as the sun climbs, leaving behind only a single, sharper number. But these measurements were not made 50 years ago. They were made now, with instruments of staggering precision by scientists who have spent decades refining their methods. The error bars are tiny. The measurements are among the most certain numbers in all of science. And those numbers, those two small, ordinary-looking numbers that you would walk past on a page, do not agree. Not by a rounding error, not by a calibration issue, not by a discrepancy that narrows when you look harder. They disagree, sharply, irreconcilably. And instead of narrowing, the gap has widened. Every refinement, every cross-check, every new instrument has only driven the numbers further apart, until the disagreement stopped being a discrepancy, until it became a discovery. The universe has told us in two different voices that it is not what we thought it was. And the gap between those voices is growing. As the measurements improved, the two numbers did not move toward each other. They held their ground. The error bars, the little margins of uncertainty around each number, grew smaller and smaller as the science got better, and the two numbers stayed stubbornly where they were, 67.4 on one side and 73.0 on the other, and the gap between them did not close. It sharpened. The better we measured, the more certain each answer became, and the more certain each answer became, the more impossible it became that they could both be right. We have now reached a point that is difficult to overstate. The chance that this disagreement is a fluke, that the two numbers are secretly the same, and we have simply been unlucky in our measurements, has fallen to less than 1 in 3.5 million. 1 in 3.5 million. That is not the language of a discrepancy. That is not a quibble between rival teams, or a problem that a little more data will smooth away. In the world of physics, odds like that are the language of discovery. They are the threshold at which scientists stop saying we think and start saying we know. But what have we discovered? We have discovered that something about our understanding of the universe is wrong. We do not yet know what. We only know, with a certainty that grows sharper every year, that when we measure the universe one way and then measure it another way, the universe gives us two different answers, and the two answers cannot both be true, and the gap between them refuses to close. This is called the Hubble tension. It is right now the deepest unsolved problem in all of cosmology. And tonight, slowly and carefully, we are going to walk through the whole strange story of it. How we learn to measure the expansion of the universe at all. The two completely separate paths that lead to the two numbers. Why those paths were supposed to meet and why they do not. And what it might mean for everything we think we know, that the most fundamental number in the science of the cosmos has quietly, stubbornly refused to agree with itself. So settle in, get comfortable, let your breathing slow. We are going to take the measure of the entire universe twice and discover that it does not add up. To understand why two numbers are tearing a hole in modern cosmology, you have to go back to the beginning, to the time before we knew the universe was expanding at all. And that time is more recent than you might think. For most of human history, nobody suspected the universe was changing at all. It was assumed to be eternal and unchanging, a fixed stage of stars that had always been there and always would be. The idea that the entire cosmos might be growing, that space itself might be stretching, would have seemed not just wrong but almost meaningless. The story of how that change begins, as so much of modern astronomy does, on a mountain in California in the early years of the 20th century. On the top of Mount Wilson near Los Angeles sat what was then the most powerful telescope in the world. Its main mirror was 100 inches across, a great disk of glass that gathered the faint light of the heavens and brought it to a focus, and it could see deeper into the dark than any human instrument before it. And working with that telescope in the 1920s was a man named Edwin Hubble. Hubble was studying the faint, fuzzy patches of light that astronomers called nebulae. These were smudges in the sky, soft and cloudy, scattered among the sharp points of the stars. Nobody was entirely sure what they were. Some thought they were clouds of gas within our own galaxy, the Milky Way, which was widely believed at the time to be the whole of the universe. Others suspected they might be something far stranger and far more distant, separate galaxies, other Milky Ways, unimaginably far away. The question was one of the great debates of the age, and it could not be settled because nobody had any reliable way to measure how far away these fuzzy patches actually were. Hubble found a way. He focused his attention on one of these patches, in particular, the one in the direction of the constellation Andromeda, then known as the Andromeda Nebula. And within it, using that great 100-inch telescope, he found a particular kind of star. A special kind, one whose properties would let him do something no one had been able to do before. He could measure its distance. We will come to exactly how these stars work later, because they matter enormously to the whole story, and they deserve their own telling. For now, it is enough to know that these particular stars act as a kind of cosmic measuring rod. By studying them carefully, Hubble could work out how far away they were. And when he did, when he calculated the distance to those stars in the Andromeda Nebula, the answer was staggering. It was far too far away to be inside the Milky Way. Andromeda was not a cloud of gas within our own galaxy. It was a separate galaxy entirely, an island of billions of stars, drifting at an enormous distance across the dark. In a single stroke, the universe had become vastly, almost incomprehensibly larger than anyone had imagined. The Milky Way was not the whole of creation. It was one galaxy among countless others, scattered through a cosmos far grander than the human mind had ever conceived. And that was only the first revelation. Because then Hubble, working with a careful and tireless assistant named Milton Humason, noticed something even more profound. They began to measure not just the distances to these galaxies, but also their motion, and they found a pattern, a relationship so clean and so startling that it would change our picture of the universe forever. The galaxies were moving away from us, nearly all of them, and the farther away a galaxy was, the faster it was receding. A galaxy twice as far away was rushing away twice as fast. A galaxy 10 times as far was fleeing 10 times as fast. The relationship was steady and proportional, distance and speed locked together in a simple rule that held across the whole sky. Now, at first, This sounds as though it should mean that we are at the center of everything, that all the galaxies are fleeing from us specifically, as though we had done something to offend them. But that is not what it means at all. And the truth is far stranger and more beautiful. The galaxies are not flying away from us through space. Space itself is expanding, swelling, stretching in every direction at once. And as it stretches, it carries all the galaxies along with it, drawing every one of them away from every other. There is no center. Every galaxy sees every other galaxy receding, and every one of them sees the same simple rule: the farther away, the faster the flight. The classic way to picture this is to imagine a loaf of raisin bread rising in the oven. The raisins are the galaxies, and the dough is space itself. As the dough rises and expands, every raisin moves away from every other raisin. A raisin sitting near another sees its neighbor drift slowly away. But a raisin on the far side of the loaf, much farther off, recedes much faster, because there is more expanding dough between them, and all of that dough is swelling at once. No raisin is at the center. The whole loaf is simply growing, and every raisin watches all the others retreat. That is our universe. Space is the dough, the galaxies are the raisins, and the whole vast loaf of the cosmos is rising. This is the discovery that gave us the expanding universe. And folded inside it is one of the most staggering implications in the history of human thought. Because if the universe is expanding now, if every galaxy is rushing away from every other, then in the past, everything must have been closer together. Run the film backward, and the galaxies draw nearer and nearer to one another. Keep running it backward, further and further into the past, and everything converges, crowding together into a smaller and smaller and hotter and denser state, until at last, at the very beginning, everything in the universe was gathered into a single, unimaginably hot and dense point. The universe, in other words, had a beginning. This is the idea we now call the Big Bang. And it was born directly out of Hubble's discovery that the galaxies are flying apart. It is hard, from this distance, to feel how radical that idea was. For all of human history before this, the universe had been imagined as eternal, a fixed and everlasting backdrop that simply was, and always had been, and always would be. The notion that the cosmos itself had a birth, a moment of beginning, a finite age, was so strange that many of the greatest scientists of the early 20th century resisted it fiercely. Some found it almost too uncomfortable to accept, too close, perhaps, to ideas they associated with myth rather than physics. There were long and bitter arguments about whether the universe truly had a beginning, or whether it had somehow existed forever in a steady, unchanging state. And it was the accumulating evidence, the expansion that Hubble found, and the ancient light that was discovered decades later that settled the matter. The universe had a beginning. It has an age. It has a history. And it is that very history, the long story of the universe from its fiery birth to the present day, that the Hubble tension now calls into question. Because, as we will see, the two ways of measuring the expansion are really two ways of reading that history, one from the near end and one from the far end. And when the two readings disagree, it is the history itself, our account of what the universe has been doing for nearly 14 billion years, that is thrown into doubt. Out of all of this came a single number, a number that captures the rate of the expansion, that tells you how fast space is stretching at the present moment. It is called the Hubble constant, in honor of the man who first measured the expansion, and it is written in the shorthand of physics as H0, H with a little zero beside it, the zero standing for now, for the present day. The Hubble constant is, at heart, a very simple idea, though it is dressed in slightly awkward units. It tells you how much faster a galaxy recedes for every additional step of distance away from us. The unit astronomers use for that step of distance is called a megaparsec, which is a great gulf of space equal to about 3.25 million light-years. And the Hubble constant tells you this: for every megaparsec of distance, a galaxy recedes faster by a certain number of kilometers every second. So if the Hubble constant is, say, 70, then a galaxy 1 megaparsec away is receding at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140. A galaxy 10 megaparsecs away at 700. The farther out you look, the faster the flight, and the Hubble constant is the number that sets the pace. It is the single number that captures the rhythm of cosmic expansion, the beat of the growing universe. And it is not just an abstract figure of interest only to specialists. The Hubble constant is one of the most important numbers in all of science, because so many other things depend on it. The age of the universe is calculated from it. If you know how fast the universe is expanding now, you can run the expansion backward and work out how long ago everything was gathered together at the beginning, how long ago the Big Bang happened. The size of the observable universe depends on it. The distances to faraway galaxies depend on it. The Hubble constant is, in a real sense, the master ruler of cosmology, the number against which a great many other measurements are calibrated. Get it right, and a whole edifice of cosmic knowledge stands on solid ground. Get it wrong, and everything built on top of it shifts. Consider just the matter of the universe's age, because it shows how much rides on this single number. The two competing values, 67 and 73, imply slightly different ages for the cosmos. A faster expansion rate means the galaxies flew apart more quickly, which means they reached their present separations in less time, which means a younger universe. A slower rate means an older one. The difference is not enormous, a matter of a few 100 million years out of nearly 14 billion, but it is not nothing either. The very age of everything, the answer to the question of how long the universe has existed, wobbles depending on which number you trust. And the age of the universe is not some idle curiosity. It has to be consistent with everything else we know. It cannot, for instance, be younger than the oldest stars we can find within it, which would be an absurdity, a universe younger than the things inside it. So the expansion rate is woven into a web of other measurements, all of which have to hang together. Pull on this one thread, and the whole web trembles, which is exactly why the disagreement matters so much. This is not some obscure parameter that only a handful of specialists care about. This is the foundation stone. And it is the foundation stone that has begun very quietly to crack. Hubble's own first attempt at measuring his constant back in the 1920s gave a wildly wrong answer, a value many times larger than what we now know to be correct. This was not because he was careless, but because the measuring rods he was using, those special stars in Andromeda, turned out to be subtler than anyone realized at the time. There were, it would later emerge, two different kinds of them, with different properties, and confusing the two threw his distances badly off. But here is the crucial thing. Even though his number was wrong, his method was sound, and the relationship he had found was real. The universe truly was expanding. The galaxies truly were flying apart in that clean, proportional way. The principle was correct. What remained was a century of painstaking work to pin down the number itself. And that work, that long quest for precision, is where our story really begins to turn. Because as scientists refined the measurement, decade after decade, sharpening their tools and narrowing their uncertainties, they would eventually arrive not at one answer, but at two. And the two would refuse to meet. The decades after Hubble were a long, slow campaign to nail down the value of his constant, and it was anything but smooth. For most of the 20th century, the measurement of the Hubble constant was a story of disagreement, revision, and fierce scientific argument. The first great correction came in the 1950s, when an astronomer named Walter Bade realized the problem with those measuring rod stars, the confusion between the two different types of them. When he sorted out the distinction, the calculated distances to the galaxies changed dramatically, and the value of the Hubble constant dropped sharply from Hubble's wildly high original figure. The universe, it turned out, was larger and older than Hubble's first numbers had suggested, and the measuring continued. Through the 1960s and 70s, the field settled into a long and famous feud. On one side stood the astronomer Alan Sandage, who had been a protege of Hubble himself and who argued after years of careful work for a low value of the constant, somewhere around 50. On the other side stood a French-born astronomer named Gerard de Vaucouleurs, who argued, with equal conviction and equal care, for a value roughly twice as high, around 100. Think about what that means. These were two of the most respected astronomers in the world, using the best available data, and they disagreed about the expansion rate of the universe by a factor of 2. One said the universe was expanding at a certain pace. The other said it was expanding twice as fast. And this disagreement, this great debate over the Hubble constant, dragged on for decades, neither side able to convince the other, the true value seemingly lost somewhere in the wide gulf between them. This was not a polite disagreement either. It was, by the standards of science, a genuinely bitter and long-running feud, the kind that shaped careers and divided the field. Sandage, in particular, was famously fierce in defense of his low value, and the argument took on something of the character of a personal rivalry, carried on across conferences and journal papers for the better part of 30 years. Younger astronomers entering the field often found themselves having to pick a side or to navigate carefully between the two camps. The whole affair became a kind of cautionary tale about how a single poorly determined number could anchor an entire scientific controversy, with each side convinced the other was making systematic errors and no clear way to prove who was right. It is worth pausing on that earlier debate because it tells us something important about the one we face today. That old disagreement, the factor of 2 argument between Sandage and de Vaucouleurs, was a disagreement born of uncertainty. The measurements simply were not precise enough. The error bars were enormous. Each side could marshal its data and make its case, but nobody could measure well enough to settle the matter for good. It was a fog, and the answer was hidden somewhere in the fog, and what was needed was a better instrument to burn the fog away. That better instrument was the Hubble Space Telescope, named, fittingly, after the very man whose constant it was built in part to measure. One of its key missions, when it launched and began its work, was to settle the great debate, once and for all, to measure the Hubble constant precisely enough that the factor of 2 argument would finally be put to rest. And around the turn of the millennium, a major project using the Space Telescope delivered its result. The Hubble constant it announced was about 72, give or take 8. For a moment, it seemed the long argument might be over. 72 sat comfortably between the warring camps, closer to de Vaucouleurs than to Sandage, but with error bars wide enough that almost everyone could find some comfort in it. The fog seemed to be lifting. The number seemed, at last, to be coming into focus. The decades of feuding appeared to have resolved into a single, sensible answer that split the difference and let everyone go home. But the error bars were the key, give or take 8. That is a wide margin, wide enough to accommodate a great many possibilities, wide enough to paper over a disagreement that had not actually gone away. The old debate did not end so much as it went quiet, waiting. And when the measurements grew sharper still, when the error bars finally narrowed in the years that followed, the disagreement would return. But it would return in a new and far more troubling form. Because the old debate had been a single method arguing with itself, a matter of not yet measuring well enough. The new disagreement would be something else entirely. It would be two completely different methods, each one measured to extraordinary precision, each one confident, each one checked and rechecked, arriving at two different answers and refusing to budge. It would not be a fog hiding a single true value. It would be two different values, each one sharp and clear, and the clarity itself would be the problem. To understand how that happened, we have to understand the two paths, the two completely separate ways that scientists have learned to measure the expansion of the universe. They begin in different places. They use different instruments. They rest on different evidence. And they were never supposed to disagree. Let us walk down the first path. The first way of measuring the expansion of the universe is called the cosmic distance ladder. And the name is exactly right, because it works just like a ladder. You cannot measure the distance to a faraway galaxy in a single step. There is no cosmic tape measure long enough. So instead, you climb. You start with something close, something whose distance you can measure directly and reliably. Then you use that nearby thing to calibrate something a little farther away. And you use that, in turn, to calibrate something farther still, climbing rung by rung, each step resting on the one below it, reaching outward into the deep universe. It is an elegant idea, and also a precarious one, because a ladder is only as sound as its rungs. If any single rung is weak, if any one step in the chain is off, then everything above it is thrown off too. The error travels up the ladder and grows. So each rung has to be built with enormous care. And the whole thing has to begin with a first step that rests on the most solid foundation imaginable. That foundation is pure geometry. It is the most reliable thing we have. The same geometry the ancient Greeks worked out with straightedge and compass, and it gives us the bottom rung of the ladder through a method called parallax. You already understand parallax, even if you have never heard the word, because your own eyes use it every moment of every day. Try this. Wherever you are, hold one finger up in front of your face at arm's length. Close one eye and look at your finger with the other. Note where it sits against the background behind it. Now switch. Close that eye and open the other. Watch what happens. Your finger appears to jump, to shift sideways against the background, even though it has not moved at all. The only thing that changed is the eye you are looking through, the position from which you are viewing. That apparent shift is parallax. And the closer the finger is to your face, the bigger the jump. Hold your finger right up against your nose and the shift is enormous. Hold it far away and the shift shrinks. So the size of the shift tells you the distance. Your brain does this automatically, comparing the slightly different views from your two eyes, and from the difference it judges how far away things are. It is how you perceive depth. It is parallax, running silently in your head, all the time. Now scale that idea up to the cosmos. Instead of two eyes a few centimeters apart, imagine two observation points on opposite sides of the great loop the Earth travels around our nearest star. The Earth circles the Sun once a year, and that orbit is enormous, about 300 million kilometers across. So if you look at a nearby star at one point in the year, and then look again 6 months later, when the Earth has swung all the way around to the other side of its orbit, You are now viewing that star from a position 300 million kilometers away from where you stood before. It is like blinking between two eyes set 300 million kilometers apart. And just like your finger against the far wall, a nearby star will appear to shift very slightly against the background of much more distant stars. Measure that tiny shift, apply the simple geometry, and you have the distance to the star. No assumptions. No chain of reasoning that could go wrong. Just the angle and the triangle, and the unbreakable rules of geometry. This is the most direct and trustworthy distance measurement in all of astronomy, and it is the bedrock on which the entire ladder stands. The shifts involved are achingly small, because even the nearest stars are tremendously far away. The angles are so tiny that for most of history we could only measure parallax for a handful of the very closest stars. But in recent years, a remarkable spacecraft has transformed this bottom rung of the ladder. A European mission called Gaia, a space telescope built for the single purpose of measuring the positions of stars with almost unbelievable precision. Gaia has measured the positions and the parallax shifts of more than 1 billion stars, with a precision so fine it is difficult to convey. It can detect angular shifts so small they are comparable to watching a coin from thousands of kilometers away and noticing it turn on its edge. It is worth dwelling on just how hard this is, because it tells you something about how far the science has come. The very first successful parallax measurement of any star was not made until the 1830s, and it was considered one of the great triumphs of astronomy at the time for a single star. After centuries of trying, the shift the astronomer measured was so minuscule that earlier observers with cruder instruments had searched for it in vain and concluded the stars must be impossibly far away, or that the Earth must not be moving at all. The shift is real, but it is fantastically small because the stars are fantastically distant. Even for the nearest star beyond our Sun, the parallax shift across the entire width of the Earth's orbit is smaller than the width of a coin seen from several kilometers off. And yet Gaia measures shifts far smaller than that, for over 1 billion stars, again and again, building a three-dimensional map of our corner of the galaxy with a precision that would have seemed like magic to the astronomers who struggled to measure even one. The bottom rung of the ladder, the geometric foundation on which everything else rests, has never been firmer. There is something fitting in that. The whole towering structure of cosmic distance measurement, reaching out to galaxies billions of light years away, rests at its base on the same simple geometry your two eyes use to judge the distance to your own hand. The triangle and the angle, the oldest trick in the book, perfected by a spacecraft. With Gaia, the bottom rung of the distance ladder became firmer than it had ever been. The foundation was set, sharper and more solid than at any point in the history of the measurement. And on that foundation, the astronomers could begin to build upward, to the second rung, to the stars that Hubble himself had used, the pulsing stars that measure the cosmos. The second rung of the ladder rests on a kind of star with a remarkable property, and on a discovery made over a century ago by a woman whose name deserves to be far better known than it is. Her name was Henrietta Swan Leavitt. In the early 1900s, she worked at the Harvard College Observatory as one of a group of women employed to do the painstaking work of examining photographic plates of the night sky and cataloguing the stars upon them. These women were called computers, in the old sense of the word, the people who did the computing, the careful measuring and calculating, in an era long before electronic machines. They were paid little and given scant credit, and yet some of the most important astronomical discoveries of the age came directly from their patient, meticulous work. And one of the greatest of those discoveries was Leavitt's. It is worth lingering on her because her story is both an inspiration and a quiet injustice. Henrietta Leavitt was assigned what was considered routine, almost menial work, the cataloguing of variable stars on photographic plates, thousands upon thousands of them, recording how their brightness changed over time. It was the kind of task that was handed to the computers precisely because it was thought to be tedious and mechanical, requiring patience rather than genius. But Leavitt, in the course of that patient work, noticed the pattern that no one had seen before. She was studying variable stars in two faint companion galaxies to our own, visible from the southern hemisphere. And because all the stars in each of those galaxies sat at roughly the same distance from us, she could compare their brightnesses directly without the confusion of distance muddling the picture. And in that controlled comparison, the relationship leapt out at her. The brighter the star, the slower its pulse. A clean, reliable law connecting rhythm to true luminosity. She published this finding in the early 1900s, and it would become one of the foundational tools of modern astronomy, the key that unlocked the scale of the universe. Edwin Hubble used her law to measure the distance to Andromeda. Astronomers have used it ever since. It is no exaggeration to say that the discovery of the expanding universe rested directly on the work of Henrietta Leavitt. And yet, in her own lifetime, she received little recognition for it. She continued her work as a computer on a modest wage and died before the full importance of her discovery was widely understood. There was talk, years later, of nominating her for a Nobel Prize before it was realized that she had already passed away and the prize is not awarded after death. Her name is far less famous than it should be. But every measurement of the distant universe, including the very tension we are exploring tonight, traces back in part to what she noticed in those photographic plates. She was studying a particular type of star, a kind that does not shine steadily but instead pulses, brightening and dimming in a regular rhythm, swelling and shrinking over and over again across days or weeks. These are called Cepheid variable stars, named after an early example found in the constellation Cepheus. A Cepheid grows bright, then fades, then grows bright again, in a steady cycle, like a slow cosmic heartbeat, like a lighthouse beam sweeping around at a fixed and faithful rate. Leavitt examined a great many of these pulsing stars, and she noticed something extraordinary. She found a clean and reliable relationship between two things. Between the rhythm of a Cepheid's pulsing, how long it took to complete one cycle of brightening and dimming, and the star's true intrinsic brightness, how much light it actually pours out. The slower the pulse, the brighter the star. A Cepheid that took many days to complete its cycle was genuinely, intrinsically more luminous than one that pulsed quickly. And the relationship was precise. Measure the rhythm, and you could calculate exactly how much light the star truly emits. Now think about why this is so powerful, because it unlocks the entire universe. Imagine you are standing in a vast dark field at night, and scattered across it are many lanterns, some near, some far. They all look like points of light, of varying brightness. The question is, which lanterns are dim because they are genuinely faint, and which are dim only because they are far away? From the apparent brightness alone, you cannot tell. A faint nearby lantern and a powerful distant one can look exactly the same to your eye. But now, suppose that every one of those lanterns announced its true brightness somehow. Suppose each one had a way of telling you exactly how much light it was really producing. Then the problem would be solved. Because if you know how much light a lantern truly emits, and you measure how bright it appears from where you stand, the difference between the two tells you the distance. A lantern that should be blazing but appears dim must be far away. The dimming is the distance. Light fades in a precise and known way as it travels, so the gap between true brightness and apparent brightness is a direct measure of how far the light has come. That is exactly what Leavitt's discovery gave us. The Cepheid variable stars announce their true brightness through the rhythm of their pulsing. Measure the rhythm, and you know how much light the star really emits. Compare that to how bright it appears in your telescope, and you have the distance. The Cepheids became cosmic lanterns of known brightness, scattered through the galaxies, each one telling you how far away it sat. This was the breakthrough that let Hubble measure the distance to Andromeda in the first place. And it remains, refined and sharpened across the decades, the crucial second rung of the distance ladder today. In our own time, the great campaign to measure the Hubble constant with Cepheids has been led by a team whose name is worth knowing, a team often referred to by the acronym SHOWS. It is led by an astronomer named Adam Rees, who had already won a share of the Nobel Prize for an earlier discovery about the universe, which we will come to in time. Rees and his team have pushed the Cepheid method to extraordinary precision. They carefully measure Cepheids in nearby galaxies, anchoring their true brightness using the geometry of parallax from the bottom rung. And then they use those Cepheids to calibrate the next rung up, reaching out toward galaxies far enough away that the expansion of the universe itself can be measured directly. Their measurement of the Hubble constant, built on this painstaking ladder of geometry and pulsing stars, comes to about 73. 73.0 to be precise, with an uncertainty of only about 1.5%. It is one of the most precise local measurements of the expansion rate ever made. But to reach all the way out into the deep universe, where the expansion truly dominates, the ladder needs one more rung. And that rung is built not on a pulsing star, but on the death of one, on the brightest stellar explosions in the cosmos. The Cepheid stars are bright, but they are not bright enough to be seen across the truly vast distances of the universe. To climb higher, to reach out into the deep cosmos where galaxies are flying apart fast enough to measure the expansion cleanly, the ladder needs a brighter beacon. It needs a lantern so luminous it can be seen across billions of light years. And the universe provides exactly such a thing in one of its most violent and spectacular events. A particular kind of exploding star. To understand it, we have to talk about what happens to certain stars when they die. We met, in our wanderings, the idea that a star like our Sun ends its life by swelling into a red giant and then casting off its outer layers, leaving behind a dense, hot, dead core called a white dwarf. A white dwarf is the ember of a dead star, an object with roughly the mass of the Sun packed into a sphere about the size of the Earth. It is extraordinarily dense, a spoonful of it weighing as much as a truck, and it sits there, slowly cooling, the quiet corpse of a star. Usually, that is the end of the story. The white dwarf simply cools and fades over unimaginable stretches of time. But sometimes, a white dwarf is not alone. Sometimes it has a companion star, the two of them orbiting each other as so many stars do. And in that case, something dramatic can unfold. The intense gravity of the dense white dwarf can begin to pull material off its companion, stealing gas from the other star, drawing it down onto itself, growing heavier and heavier as it feeds. But a white dwarf cannot grow heavier without limit. There is a threshold, a critical mass, beyond which it simply cannot hold itself together. This limit has a precise value, a little under 1.5 times the mass of our Sun, and it is one of the firmest numbers in all of stellar physics. As the white dwarf feeds on its companion and creeps toward that limit, it approaches a point of no return. And when it crosses that threshold, it can no longer support itself against its own gravity, and it detonates. The entire white dwarf is consumed in a single colossal thermonuclear explosion, a blast so brilliant that for a few weeks it can outshine an entire galaxy of billions of stars. This is called a Type 1a supernova. And here is the crucial thing. The thing that makes these explosions so valuable for measuring the cosmos. Because every one of these white dwarfs detonates at very nearly the same critical mass, that same firm limit a little under 1.5 times the mass of the Sun, every one of these explosions releases very nearly the same amount of energy. They all blaze with very nearly the same true brightness. They are, in effect, standard candles, cosmic explosions of known luminosity going off across the universe. There is something almost too convenient about this, and it is worth appreciating why it works. Most exploding stars are not standard at all. The other main kind of stellar explosion, the kind that comes from the collapse of a single massive star, varies enormously in brightness from one event to the next, depending on the size and nature of the star that died. You cannot use those as measuring rods because you never know how bright any individual one truly was. But the Type 1a supernovae are different, and the reason is that trigger, that universal threshold. Because they all detonate when they reach the same critical mass, they all begin from nearly the same starting conditions, and so they all produce nearly the same blast. It is as though the universe had manufactured a vast supply of identical flashbulbs and scattered them across the cosmos, each one going off with the same known brilliance, perfect for measuring distance. In practice, they are not quite perfectly identical, and this is where the care comes in. There are small variations from one to the next, but astronomers discovered something wonderful, a pattern that lets them correct for the differences. The explosions that are intrinsically a little brighter also fade more slowly, and the ones that are a little dimmer fade more quickly, and the relationship between the brightness and the rate of fading is reliable enough that, by watching how quickly a given supernova dims, astronomers can work out exactly how bright it truly was. With that correction applied, the Type 1a supernovae become exquisite standard candles, their true brightness known to within a few percent. And because they are so brilliant, briefly outshining entire galaxies, they can be seen across enormous distances, far out into the deep universe where the expansion runs free. Think back to the lanterns in the dark field. A Type 1a supernova is like a lantern that always shines with the same known power, but a lantern so bright it can be seen from the far side of the field, from across the whole vast cosmos. Because we know how brightly these explosions truly shine, we can measure how bright they appear from Earth. And the difference gives us the distance, even when that distance is billions of light years. There are subtle refinements to this, careful corrections that account for small variations between one explosion and another, but the principle holds. These dying stars are the brightest, reliable measuring rods we have, and they form the topmost rung of the distance ladder. So now we can see the whole ladder, standing complete, reaching from our backyard out to the depths of the cosmos. At the bottom, the solid bedrock of geometry, parallax, the apparent shift of nearby stars measured with exquisite precision by the Gaia spacecraft. Resting on that, the pulsing Cepheid stars, their true brightness revealed by their rhythm, calibrated against the geometry below. And resting on those, the brilliant exploding stars, the Type 1a supernovae, calibrated by the Cepheids and reaching out into the deep universe where the expansion runs free. Each rung resting on the one below, each step calibrated by the last. The whole structure reaching from the Earth's orbit to the edge of the observable cosmos. And when you climb that ladder all the way to the top, When you measure the distances to those far galaxies and compare them to how fast they are receding, you arrive at a value for the Hubble constant. You arrive at the rate of cosmic expansion, measured directly, locally, by stepping outward through the present-day universe. The ladder's answer is about 73. Now, a single measurement, however careful, can always be questioned. Perhaps there is some flaw hidden in the ladder. Perhaps one of the rungs has a subtle problem, some systematic error that throws the whole thing off. This is exactly the kind of worry that keeps careful scientists humble. And so the natural question is, can we check the ladder's answer some other way? Can we measure the local expansion rate by a method that does not depend on Cepheids and supernovae to see if it agrees? We can, and this is where the story takes on real weight, because the ladder is not alone. There are several other ways to measure the expansion rate of the local universe, methods that are largely or entirely independent of the Cepheid ladder, that rest on different stars, or different physics, or different geometry altogether. And the remarkable thing, the thing that transforms this from one team's result into something far more solid, is that these other methods broadly agree with the ladder. There is a method that uses a different kind of star altogether, the brightest red giant stars in a galaxy, which reach a sharp and predictable peak in brightness that can serve as its own kind of standard candle independent of the Cepheids. When astronomers measure the expansion rate this way, they get a number a little lower than 73, but close, in the same neighborhood, consistent within the uncertainties. There is a method that uses the way the surface brightness of distant galaxies flickers and varies, which depends on their distance in a measurable way. It lands in the same range. There is a beautiful and entirely independent method that uses certain rare galaxies containing natural cosmic lasers, intense beams of microwave radiation from clouds of gas orbiting their central black holes. By tracking the motion of these clouds, astronomers can work out a direct geometric distance to the galaxy, with no ladder at all, no chain of calibration, and the expansion rate it yields is close to 74, right in line with the ladder. This maser method deserves a moment because it is one of the cleanest measurements we have, and it sidesteps the ladder entirely. In certain special galaxies, there are clouds of water vapor orbiting close to the central black hole, and the intense conditions there cause them to emit powerful, focused beams of microwave radiation, natural lasers operating on a cosmic scale. By watching how these glowing clouds move as they orbit, measuring their speeds, and how those speeds change, astronomers can map out the geometry of their orbits directly. And from that geometry, using nothing but careful observation and basic physics, they can calculate exactly how far away the galaxy is. It is a pure, direct, geometric distance, owing nothing to Cepheids or supernovae or any rung of the ladder. It stands entirely on its own, and it agrees with the ladder, landing near the high value. And there is a method that uses one of the strangest predictions of Einstein's theory of gravity, the bending of light by mass. When the light from a distant bright object passes by a massive galaxy on its way to us, that galaxy's gravity bends and splits the light, sometimes producing multiple images of the same distant object. And because the different paths the light takes are of slightly different lengths, flickers in the distant object arrive at slightly different times in the different images. By measuring those time delays, astronomers can work out distances across the universe, and from them, the expansion rate. This method, too, lands near 73. It is worth dwelling on how strange and wonderful that lensing method is, because it turns Einstein's theory into a measuring tool. If a very distant bright object, such as a brilliant beacon at the heart of a far galaxy, happens to sit almost directly behind a massive foreground galaxy, The gravity of that foreground galaxy bends the passing light, the way a lens bends light, and can produce several separate images of the same background object spread around the sky. Now suppose that background beacon flickers, brightening and dimming over time. The flickers show up in each of the separate images, but not at the same moment, because the light forming each image took a different path of a slightly different length to reach us, and so arrived a little earlier or a little later. By carefully timing those delays between the images and modeling the geometry of the lens, astronomers can deduce the absolute scale of the distances involved, and from that, the expansion rate of the universe. It is an entirely separate path, resting on gravity and timing rather than on standard candles, and it too comes out near the high value of the ladder. So the ladder's answer is not a lonely voice. It is part of a chorus, several independent methods resting on different physics and different objects, looking at the local present-day universe, all converging on roughly the same number, around 73. When you measure the expansion of the universe by looking outward at the galaxies as they are now, in the cosmos around us, the answer comes back again and again near 73. That is the first number. That is the first voice. Hold it in your mind, because now we are going to measure the very same universe by a completely different method. A method that does not climb any ladder, that does not use any nearby star, that looks not outward into the present but backward, across nearly the entire history of the cosmos, to the oldest light there is, and it will give us a different number. The second path does not begin with a nearby star. It begins at the beginning, with the oldest light in the universe, light that has been traveling since the cosmos was young, carrying within it a message about what the universe was like in its infancy. To understand this light, we have to go back to the early universe, to a time not long after the Big Bang. In its first few 100,000 years, the universe was a very different place from the vast, dark, transparent cosmos we see today. It was unimaginably hot and dense, a blazing fog of matter and energy crushed together. It was so hot that atoms could not even form. The building blocks of matter, the electrons and the atomic nuclei, were torn apart by the heat, flying free in a thick, glowing plasma. And in that dense plasma, light could not travel. Every time a particle of light tried to move, it almost immediately ran into one of the free-flying electrons and scattered off, bouncing this way and that, unable to get anywhere. The universe was opaque, a glowing fog, impenetrable to light. But the universe was expanding, and as it expanded, it cooled. And about 380,000 years after the beginning, it reached a turning point. It had cooled just enough, to a few thousand degrees, for the electrons and nuclei to come together at last and form complete, neutral atoms. And the moment they did, everything changed. With the electrons now bound up in atoms, no longer flying free to scatter the light, the fog cleared. Space became transparent, and the light that had been trapped, bouncing endlessly in the plasma, was suddenly set free to travel in straight lines across the cosmos. It is worth pausing to picture that moment because it is one of the most important transitions in the entire history of the universe, and it happened everywhere at once. Imagine the whole cosmos, in every direction, as a thick and glowing fog, so dense that you could not see your hand in front of your face, light scattering uselessly in every direction. And then, over a relatively brief span, as the temperature dropped past that critical threshold, the fog clears everywhere, all at once. The universe goes from opaque to transparent. For the first time, light can cross open space freely. It is sometimes described as the moment the universe became visible to itself, the moment the cosmic fog lifted and the light was released to begin its long journey. Every photon of the cosmic microwave background we detect today began its travels at that single transition, set free as the fog cleared, and has been traveling ever since, untouched, across nearly the whole age of the universe, until it finally lands in our instruments. That light has been traveling ever since. For nearly 14 billion years, it has streamed across the expanding universe, and it is still arriving even now from every direction at once. It is the afterglow of the hot, early universe, released at the moment the fog lifted and it fills all of space. We call it the cosmic microwave background, and it is, in the most literal sense, a baby picture of the universe. A snapshot of what the cosmos looked like when it was just 380,000 years old, light that has been traveling toward us across almost the entire age of existence. There is something to dwell on in that. When you detect the cosmic microwave background, you are not looking at a recreation or a model or an inference. You are looking at actual light, real photons that were emitted when the universe was a few 100,000 years old and have been traveling toward you undisturbed ever since. It is the oldest thing you can ever observe. There is nothing older to see, because before that moment, the universe was opaque and no light could escape to carry a picture of it. The cosmic microwave background is, quite literally, the edge of the visible past, the furthest back in time that light itself allows us to look. To measure it is to look directly at the infancy of everything. But this light has changed on its long journey. When it was first set free, it was the glow of a fog a few thousand degrees hot. But over nearly 14 billion years, the expansion of the universe has stretched it. As space itself swelled, it stretched the waves of this ancient light along with it, drawing them out longer and longer, draining their energy, cooling them. And so today, that once fiery glow has been stretched all the way down into faint microwaves, corresponding to a temperature of just under 3 degrees above absolute zero. The fire of the early universe, cooled by billions of years of cosmic expansion, has become the faintest possible whisper of warmth, filling all of space. And here is the thing that makes this ancient light so precious to science. It is almost perfectly uniform. Whichever direction you look, the cosmic microwave background glows at very nearly the same temperature, astonishingly even across the entire sky. But not perfectly even. When you measure it with sufficient care, you find tiny variations, faint patches that are very slightly warmer or very slightly cooler than the average. Differences of about 1 part in 100,000. Minuscule ripples in the temperature of the ancient light. Those tiny ripples are among the most important features in all of cosmology, because they are a map of the seeds of everything. Those faint patches of slightly denser and slightly less dense material in the early universe were the beginnings of all cosmic structure. The slightly denser regions had slightly more gravity, and over billions of years they pulled in more and more matter, growing into the galaxies and the clusters of galaxies that fill the universe today. Everything we see, every galaxy, every star, every world, grew from those faint ripples in the primordial fog. The cosmic microwave background is a picture of the universe in its infancy, with the seeds of all that would come already faintly visible within it, and encoded in the precise pattern of those ripples, in their sizes and their spacing and their arrangement across the sky, is an astonishing amount of information about the early universe. If you can read that pattern carefully enough, it tells you what the universe was made of, how much ordinary matter and how much dark matter, and how much of the mysterious dark energy and how fast it was expanding, and a great deal more. The ripples are a kind of cosmic text, written in the oldest light waiting to be read, To understand how a pattern of warm and cool patches can possibly contain all of this, it helps to think about sound. In the hot plasma of the early universe, before the fog lifted, the whole cosmos rang like a struck bell. Pressure waves, which is to say sound waves, rippled through the dense glowing matter. These were not sounds anyone could have heard, but they were sound waves nonetheless, regions of compression and rarefaction sweeping through the primordial plasma. And just as the particular sound of a bell or a drum tells you something about its size and shape and material, the pattern of these primordial sound waves, frozen into the ancient light at the moment the fog cleared, tells us about the universe that produced them. The characteristic sizes of the warm and cool patches correspond to the characteristic wavelengths of those frozen sound waves. And from those sizes, cosmologists can deduce the composition and behavior of the early cosmos with remarkable precision. In a very real sense, the cosmic microwave background is a recording of the sound of the early universe, and reading it is like listening to the faint, frozen echo of the cosmos ringing in its infancy. And in our time, we have built an instrument to read that recording with breathtaking precision. To read the faint ripples in the cosmic microwave background, you need an extraordinarily sensitive instrument, one that can measure tiny differences in temperature across the whole sky, differences of 1 part in 100,000. And you need to get above the interference of the Earth's atmosphere. So the finest measurements of the ancient light have come from spacecraft, and the most precise of them all came from a European satellite called Planck, which spent several years in the early 2010s patiently mapping the cosmic microwave background across the entire sky at many different wavelengths at once, with a precision never achieved before. What Planck produced was the most detailed map of the ancient light ever made. And from that map, cosmologists could read the pattern of the ripples in extraordinary detail. They could measure not just that the ripples existed, but their precise statistical pattern, the way the temperature variations were distributed across different sizes and scales. This pattern has a particular shape, with a series of features that scientists can analyze with great care, and each feature carries information about a different property of the early universe. We do not need to follow every technical detail to grasp the essential idea. What matters is this: hidden in the pattern of those ripples is a kind of cosmic ruler, a known physical scale set down in the early universe. In the hot plasma before the fog lifted, sound waves rippled through the cosmos, pressure waves traveling through the dense matter, and they traveled a certain characteristic distance before the fog cleared and froze them in place. That characteristic distance, the size of those frozen sound waves, is a length we can calculate from physics, a known standard built into the early universe. And it shows up in the pattern of the ripples as a characteristic size, an angular scale stamped across the ancient sky. Now here is the elegant part. We know how big that ruler truly was in the early universe from physics, and we can measure how big it appears to us now, projected across the sky. The difference between the two, the true size and the apparent size, tells us about the geometry and the expansion history of the universe in between. By measuring that ancient ruler and feeding it into our best model of how the universe evolves, we can work out what the universe was made of and how it has expanded across all the time since. And from that, we can calculate what the expansion rate should be today. This is the crucial thing to understand about the second path. It does not measure the expansion rate directly, here and now, the way the ladder does. Instead, it measures the universe as it was, in its infancy, with great precision. And then it uses our best theory of how the universe works, our standard model of cosmology, to project that early universe snapshot forward across nearly 14 billion years, all the way to the present day. It asks, in effect, given exactly what the universe was like back then, And given everything we understand about how it evolves, how fast should it be expanding now? This distinction is the heart of everything, so it is worth making it as vivid as possible. Imagine you are watching a film of a thrown ball, but you are only allowed to see the very first frame, the instant the ball leaves the hand. From that single frame, if you know the laws of physics, the speed and angle of the throw, the pull of gravity, the resistance of the air, you can calculate exactly where the ball should be at every later moment. You can predict from that first frame alone where it will land. The early universe method is like that. It sees the first frame, the ancient light, with extraordinary clarity, and then it uses the laws of physics, our model of the cosmos, to calculate where everything should be now, including how fast the expansion should be running. The distance ladder, by contrast, is like watching the final frame directly, seeing where the ball actually is at the end, measuring its present position and motion with your own eyes. And here is the problem. The prediction from the first frame and the direct measurement of the last frame do not match. The ball is not where the laws of physics say it should be, given how it was thrown. Either we have misjudged the throw, or we have misjudged something about the flight, the gravity or the air, or some force acting on the ball that we have not accounted for. Something between the first frame and the last is not what we think it is. That is precisely the situation cosmology faces. The early universe, projected forward, predicts one expansion rate. The late universe, measured directly, shows another. And the gap between them means our account of the flight, the history of the cosmos in between, is missing something. The standard model of cosmology, the framework used to make this projection, is a tremendously successful theory. It describes a universe made of ordinary matter, plus a large amount of invisible dark matter, plus an even larger amount of mysterious dark energy that drives the expansion to accelerate. This model has passed test after test. It explains a vast range of observations with remarkable accuracy. It is one of the great achievements of modern science. And when you take Planck's exquisite measurement of the ancient light and run it forward through this trusted model, you get a prediction for the expansion rate today. That prediction is about 67. 67.4 to be precise, with an uncertainty of less than 1%. It is one of the most precise determinations of the expansion rate ever made, every bit as careful and rigorous as the ladder, resting on completely different evidence and completely different methods. 67.4 from the ancient light projected forward. 73.0 from the ladder reaching outward, and there it is. Two of the most precise measurements in the history of science aimed at the same single quantity, the expansion rate of the one universe we live in, built by different people, on different evidence, with different instruments, sharing not a single assumption. And where they should have met, they stand apart. Let us sit with the gap, because the whole crisis lives inside it. The difference between the two numbers is a little over 5 in the units cosmologists use, and your first instinct might be that this is a small difference, 67, 73. They are not so far apart. Surely a gap that small is nothing to lose sleep over. But it is not the size of the gap that matters. It is the size of the gap compared to the precision of the measurements. And both measurements are now extraordinarily precise. The ladder's answer of 73 has an uncertainty of only 1% or so. Planck's answer of 67 has an uncertainty smaller still. Each number is pinned down tightly, hemmed in by small hard-won error bars, and the two error bars do not overlap. They do not come close to overlapping. There is a clear, empty gulf between them, a no man's land where neither measurement says the answer should be. This is the crucial point, and it is worth making it slowly. A disagreement between two rough measurements means nothing, because their uncertainties are wide and they overlap, and the truth could comfortably sit in the shared middle ground. But as two measurements grow more precise, their uncertainties shrink. And if they are truly measuring the same thing, they should close in on each other, their narrowing ranges still overlapping around the common answer. That is not what these two have done. They have grown more precise. Their ranges have shrunk, and the shrinking ranges have pulled apart, each one tightening around a different value with nothing but empty space between them. Precision was supposed to bring them together. Instead, precision has driven them apart. The sharper our vision becomes, the more clearly we see that they simply do not agree. Scientists have a way of measuring how serious a disagreement like this is, a way of expressing how unlikely it is that the gap is just an unlucky accident. They count it in units called sigma, standard deviations, a measure of how far apart two results are compared to their uncertainties. A disagreement of 2 sigma is mild, the kind of thing that often turns out to be a fluke. 3 sigma is interesting, worth a second look. 4 sigma is serious. And 5 sigma is the gold standard, the threshold at which physicists are willing to announce a genuine discovery, because the odds of it being mere chance have become vanishingly small. The disagreement between the two measurements of the Hubble constant has now crossed 5 sigma, and it did not get there all at once. This is part of what makes it so compelling and so troubling. You can trace its growth over the years. A decade or so ago, the gap was around 2 sigma, mild enough that most people assumed it would close as the measurements improved. But it did not close. As the measurements sharpened, the gap grew to 3 sigma, then to 4, and now past 5. Every improvement in precision, on both sides, has driven the two numbers further apart in significance, not closer together. The disagreement has not faded under scrutiny. It has hardened. And here is the meaning of that 5 sigma mark made concrete. It is the same standard of proof that physicists demanded before they would announce the discovery of new particles, the level of certainty reserved for genuine landmark findings. To cross it is to leave behind the realm of probably and enter the realm of as good as certain. By that standard, the disagreement between these two numbers is no longer a suspicion or a worry. It has the same statistical weight that physicists treat as a discovery. The difference is that a normal discovery announces something new and understood, a particle found, a prediction confirmed. This one announces only that something is wrong, that two careful measurements of the same universe cannot be reconciled, and that we do not yet know why. Let that settle here in the quiet. These are two of the most carefully made measurements in all of science. Independent teams, using independent methods, checking and rechecking their work for years, hunting down every possible source of error. And the universe, measured one way, says 67. Measured another way, it says 73. The disagreement has reached the level that science treats as proof, and yet what it proves is not an answer but a problem. For a long time, the hope was that someone would find a mistake, that somewhere in the ladder, or somewhere in the reading of the ancient light, there was a hidden error, a subtle flaw that once found and corrected would bring the two numbers together and end the crisis. And people have searched exhaustively for exactly such a flaw. The Cepheid measurements have been scrutinized for any hint of contamination or miscalibration. The supernova methods have been checked and rechecked. The reading of the ancient light has been examined from every angle. New instruments, including the powerful new space telescopes of our era, have been turned on the problem specifically to look for errors in the ladder. And the errors have not been found. Instead, the measurements have only grown more confident. The new observations have tightened the ladder's answer, not loosened it. The gap has not been explained away. It has been confirmed again and again from both directions, which leaves us facing a conclusion that is difficult to escape and difficult to sit with. We have measured the universe twice. We have measured it with enormous care, by two completely independent methods, and the universe has given us two different answers. And the difference between them is now, statistically, almost indistinguishable from certain. If it is not a mistake, then it is something else. It is a sign, a signal that something in our understanding of the universe, somewhere between the ancient light and the present day, is missing or wrong. Because remember what the second method actually does. It does not measure today's expansion directly. It measures the early universe, and then projects forward using our best model of how the cosmos evolves. So, if that projection comes out wrong, if it predicts 67 when the universe is actually doing 73, then perhaps the problem is not in the measurement at all. Perhaps the problem is in the model. Perhaps something happened in the 14 billion years between the ancient light and now that our model does not know about. And that possibility opens a door onto something genuinely thrilling and genuinely unsettling. The possibility of new physics, of some ingredient in the universe, some force or substance or process that we have not yet discovered, quietly making itself known through the one place it cannot hide, the gap between two numbers. So let us turn to the suspects. Let us ask, what could possibly be hiding in that gap? If the disagreement is real, and it increasingly seems that it is, then something is wrong with the story we have been telling about the universe. And the most natural place to look for the missing piece is in the part of the story we understand least: the dark sector. The mysterious ingredients that make up most of the cosmos and that we barely understand at all. Before we meet the suspects, it is worth pausing on a humbling fact, because it frames everything that follows. The ordinary matter that makes up you and the earth and the stars and everything you have ever seen or touched accounts for only about 5% of the universe. The other 95% is made of two things we cannot see and do not understand. About a quarter of the universe is dark matter, an invisible substance that we detect only through its gravity, that holds galaxies together but emits no light and has never been directly identified. And the remaining 70% or so is something even stranger, called dark energy, a mysterious pressure that seems to be pushing the universe to expand faster and faster, and whose nature is one of the deepest mysteries in all of science. So when we say we have a model of the universe, we should be honest about what that means. We have a model that works beautifully, that fits a vast range of observations, but that is built on top of two enormous question marks. Dark matter and dark energy are, in a sense, names for our ignorance, labels we have placed on things we know are there but do not understand. And so it should not be entirely surprising if the first real crack in our model turns out to involve exactly these mysterious ingredients. If something is hiding in the gap between the two numbers, the dark sector is where it most likely lurks. It is genuinely worth sitting with the strangeness of this situation, because we have grown so used to it that we forget how bizarre it is. We have built the most precise and successful model of the cosmos in human history, a model that predicts the pattern of the ancient light to exquisite accuracy and explains the distribution of galaxies across billions of light years. And yet that model tells us that almost everything in the universe is made of substances we have never identified and do not comprehend. Imagine a scientist who could predict the behavior of the oceans with perfect accuracy, the tides and the currents and the waves, but who had to admit that 95% of the water was made of a substance no one had ever seen or could name. That is roughly our position with the cosmos. The success is real, and so is the ignorance side by side. We can describe what the dark universe does with great precision, while having essentially no idea what it actually is. Given that, the Hubble tension takes on a particular significance. It may be the point where our ignorance of the dark sector finally becomes visible, where the things we have merely named without understanding begin to reveal their true behavior. The mysterious ingredients have been sitting quietly in our equations, doing their work, fitting the data. But if one of them is not quite what we assumed, if dark energy is not perfectly constant, or dark matter not perfectly simple, then the place that discrepancy would first show up is exactly here, in a careful comparison of the early universe with the late one. The gap between the two numbers may be the dark sector clearing its throat. The first and cleanest suspect is an idea called early dark energy. The reasoning behind it is subtle but elegant, so let us take it slowly. Remember how the second method works. It measures the ancient light, and in particular the size of that cosmic ruler, the frozen sound waves stamped into the early universe. The apparent size of that ruler depends on how the universe expanded. Now, the puzzle is that the ancient light method predicts a lower expansion rate today than the ladder measures. One way to fix that, to reconcile the two, would be if the ruler itself were actually a little smaller than we assume. Because if the ruler was smaller, then reading it would lead us to a higher expansion rate, closer to the ladder's 73. And what could make the ruler smaller? If there was some extra ingredient in the very early universe, some additional source of energy that existed briefly around the time the fog lifted and then faded away, it would have made the early universe expand a little faster during that crucial window. And that faster early expansion would have given those frozen sound waves less time to travel, making the ruler a little shorter. A shorter ruler would mean a higher expansion rate today. The two numbers might be brought into agreement. This hypothetical extra ingredient is called early dark energy, a burst of dark energy in the infancy of the cosmos, present for only a brief time and then vanishing. It is an attractive idea because it could close the gap with a single new ingredient. But it has problems. The simplest versions of the idea are now in trouble, squeezed by other observations. When you add early dark energy to make the two Hubble numbers agree, it tends to throw off other features of the ancient light, creating new disagreements even as it resolves the old one. More elaborate versions remain possible, but the room for them is narrowing as the measurements improve. Early dark energy is a suspect with a plausible motive, but the evidence against it is mounting. The second suspect lives not in the early universe, but in the late one. Not in the infancy of the cosmos, but in its recent history, and perhaps its future. And it concerns the nature of dark energy itself, the mysterious force driving the expansion to accelerate. In our standard model, dark energy is assumed to be something very particular. It is assumed to be constant, a fixed property of empty space itself, the same density everywhere and at every time, never changing as the universe evolves. This is the simplest possible assumption, and for a long time it fit the data well. Dark energy, in this picture, is a steady, unchanging pressure, woven into the fabric of space, pushing outward at the same rate forever. But what if that assumption is wrong? What if dark energy is not constant at all? What if its strength changes over time? This is a live possibility, and recent observations have begun to hint, tantalizingly, that it might even be true. A major survey of the universe, mapping the positions of millions of galaxies to trace how cosmic expansion has changed over billions of years, has produced results that seem to point gently but persistently toward a dark energy that is not constant. That may be evolving. That may have been somewhat different in the past than it is today. The evidence is not yet conclusive. It is the kind of hint that makes scientists lean forward, not the kind that settles the matter. But it is there, and it is being watched very closely, because if dark energy does change over time, it would be a profound discovery in its own right, and it might also bear on the Hubble tension. To feel why this would be such a big deal, consider what it would overturn. For decades, the simplest and most elegant assumption was that dark energy is what physicists call a cosmological constant, an idea that traces all the way back to Einstein himself. A cosmological constant is, as the name says, constant. The same density of dark energy in every cubic meter of space, unchanging from the beginning of the universe to its end. It is the tidiest possible assumption, requiring just a single fixed number, and for a long time the data gave no reason to doubt it. The universe behaved as though dark energy were exactly this kind of fixed, eternal property of empty space. If the new hints hold up, that tidy picture would have to go. Dark energy would become something dynamic, something with a history, a force that was stronger or weaker in the past and is changing still. And that would open a vast new set of questions. What is dark energy that it can change? What governs how it evolves? Is it some kind of field that fills all of space and shifts over cosmic time rather than a fixed constant? We would have traded a single mysterious number for an entire mysterious process, and the depth of our ignorance about the dominant ingredient of the universe would be laid bare. It is the kind of development that could reshape cosmology for a generation, and the early hints of it are part of what makes this moment in the science feel so charged. We may be watching the simplest assumption about the universe quietly begin to fail. There is a particularly dramatic version of this idea, in which dark energy grows stronger as the universe ages, its push intensifying over time. If dark energy were to behave this way, it would have unsettling implications for the distant future. Because a dark energy that strengthens without limit would eventually overwhelm everything. It would expand the universe not just faster and faster, but so violently that it would begin to tear apart the structures within it. First, the galaxies would be ripped from one another. Then individual galaxies torn apart. Then solar systems, then planets, and finally, in the last moments, the very atoms themselves shredded as space expanded faster than anything could hold together. This hypothetical fate has a name. It is called the Big Rip, and there is a haunting thought folded into this possibility. If the Hubble tension is caused by a dark energy that grows over time, then the very same force that is making our two measurements disagree, the force we are detecting through this strange gap in our numbers, would be the force that is destined, in the unimaginably distant future, to tear the universe apart. The discrepancy in our measurements would be the first faint whisper of the ending of everything. This is far from certain, only one possibility among several. But it is a striking reminder that a small disagreement between two numbers can, if you follow it far enough, open onto the largest questions there are. Early dark energy and evolving dark energy are the leading suspects, but they are far from the only ones. The Hubble tension has drawn the attention of theorists across cosmology, and they have proposed a whole menagerie of possible explanations, each one a guess at what might be hiding in the gap. Perhaps the problem lies with dark matter. We have always assumed that dark matter is, in the jargon, cold, meaning that its particles move slowly and interact with one another only through gravity. But what if dark matter, is more complicated than that. What if dark matter particles can interact with each other in some hidden way, or can decay over time into other things, or can talk to some unseen form of radiation? Various such ideas have been proposed, and some of them could, in principle, nudge the expansion history of the universe in ways that might ease the tension. Perhaps the answer lies with the ghostly particles, called neutrinos, the faint, nearly massless particles that stream through the universe in enormous numbers. We know of 3 types of neutrino, but what if there were a 4th, a hidden kind that interacts even more weakly than the others through gravity alone? Such an extra particle would have altered the early universe in subtle ways, and some have wondered whether it could play a role in the puzzle. Or perhaps the problem is more radical still. Perhaps the issue is not with the contents of the universe at all, but with our theory of gravity itself. Our understanding of gravity rests on Einstein's general theory of relativity, one of the most beautifully confirmed theories in all of physics, tested again and again and never found wanting. But it has been tested most rigorously on relatively small scales within our solar system and in the behavior of things like merging black holes. What if, on the very largest scales, the scale of the entire cosmos, gravity behaves slightly differently than Einstein's theory predicts? A whole family of alternative theories of gravity has been proposed over the years, and some have been examined for whether they might resolve the tension. But here is the uncomfortable truth that runs through all of these ideas. None of them works cleanly. Each proposed solution, when examined closely, tends to fix the Hubble tension only by creating some new problem elsewhere, some fresh disagreement with the wealth of other observations we have. The standard model of cosmology, for all that it may be incomplete, is extraordinarily successful, and it is woven tightly together. You cannot simply pull on one thread to fix one problem without unraveling something else. Every suspect so far has an alibi for some other crime. The tension stubbornly resists every elegant solution thrown at it, and that resistance is itself a clue. It suggests that whatever is going on may be more subtle or more surprising than any of our current guesses, which brings us to the most unsettling possibility of all. There is one possibility we have not yet fully confronted, and it is in some ways the most disturbing of all, because it does not point to a mistake in either measurement. It accepts both. What if both numbers are correct? What if the universe really was on track to expand at 67, based on its condition in infancy, and really is expanding at 73 today, and there is no error in either finding? What if the early universe and the late universe genuinely disagree, not because we measured something wrong, but because something happened in between that we do not understand? What if the expansion rate truly did change, in some way that our smooth, simple model cannot capture? Consider what the second method really assumes. It takes the early universe and projects it forward across nearly 14 billion years using a single, smooth, continuous model, a model in which the universe evolves steadily from then to now along one unbroken trajectory. But what if that trajectory was not smooth? What if the history of the universe contains a chapter or several chapters that our model knows nothing about? Some episode, some transition, some event in the dark sector that nudged the expansion onto a different track partway through, leaving the early universe and the late universe genuinely out of step, connected by a history more complicated than our equations allow. In this view, the Hubble constant was never really constant at all. The very name would be a kind of mistake, a holdover from a simpler picture. The expansion rate would be something that changed over cosmic history, perhaps not smoothly, but in steps, shaped by physics we have not yet discovered. And the tension between our two numbers would not be a problem to be explained away, but a genuine discovery. The first solid evidence that the universe has a richer, stranger history than our model can read. If that is true, then we have been doing something subtly mistaken for a long time. We have been projecting a single, simple story onto a universe whose real history may contain multiple chapters, twists we cannot see, events that left no trace, except this one stubborn gap between two carefully measured numbers. We have been reading the universe as if it were a straight line from beginning to now, when it may, in truth, be a far more complicated tale. And remember, once more, how little we actually understand of what the universe is made of. 95% of it is dark, mysterious, unidentified. We have named the darkness, but we have not understood it. The Hubble tension may be the first real crack in the smooth surface of our ignorance, the first place where the hidden complexity of the dark universe is pushing through into the light, making itself known through the one signal it cannot suppress, the disagreement of two numbers that should have matched. That is a thrilling thought and a humbling one. It suggests that we are standing at the edge of something, that this small, stubborn gap may be the doorway to a deeper understanding of the cosmos, a clue to physics we have not yet imagined. The history of science is full of moments exactly like this one, when a tiny, nagging discrepancy that everyone wished would just go away turned out instead to be the loose thread that, when pulled, unraveled an old picture of the world and revealed a new one beneath. Consider how often this has happened before. In the late 19th century, physicists believed they had very nearly finished the job, that the great structure of physics was essentially complete, with only a few small details left to tidy up. Among those small details were a couple of nagging experimental results that did not quite fit, minor discrepancies that seemed like loose ends. One concerned the strange behavior of light and the apparent absence of a medium for it to travel through. Another concerned the peculiar way that hot objects glow. These were regarded as small puzzles, embarrassments to be cleared up. Instead, pulling on those two threads unraveled the whole of classical physics and gave us, within a few decades, the two great revolutions of the 20th century, relativity and quantum mechanics. The small discrepancies were not loose ends at all. They were the visible tips of entirely new physics, hidden beneath the surface of a picture that had seemed complete. There is a recurring lesson in this. The most important discoveries often do not arrive with fanfare, as bold new predictions triumphantly confirmed. They arrive quietly, as small disagreements that refuse to resolve, as numbers that stubbornly fail to match, as anomalies that everyone initially assumes must be a mistake. The greatness of the discovery is often invisible at first, disguised as a mere annoyance. And the scientists who change the world are frequently the ones who refuse to look away from the annoyance, who keep worrying at the thread that everyone else wishes would simply tie itself off. The Hubble tension may be precisely such a thread. For years, the hope was that it would resolve itself, that it was a mistake waiting to be found. That hope has steadily faded. The disagreement has only sharpened. And so, more and more, cosmologists have begun to take seriously the possibility that they are looking at one of those world-changing threads, a small, stubborn fact that, when finally understood, will force a deep revision of our picture of the cosmos. We cannot yet see what the new picture will look like. We can only see the crack in the old one and feel with growing conviction that there is something real and important on the other side of it. So let us pull back now and ask what it means when the most fundamental ruler in all of cosmology begins to break, and whether this lonely crack is truly alone, or whether there are others. If the Hubble tension stood entirely alone, a single strange disagreement In an otherwise flawless picture, it would be easier to dismiss. A lone anomaly can always, in principle, turn out to be some subtle mistake not yet found. But the Hubble tension does not stand alone. And this is perhaps the most important thing to understand about why cosmologists take it so seriously. It is not the only crack in the model. It is one of several. There is a second tension, less famous than the Hubble tension but real, that concerns how clumpy the universe is. Our standard model, fed with the measurements from the ancient light, makes a prediction about how much the matter in the universe should have clumped together over cosmic time, how strongly it should have gathered into galaxies and clusters, and the great cosmic web of structure. And when astronomers measure the actual clumpiness of the universe directly by surveying how matter is distributed across the sky, they find that the universe is slightly less clumpy than the model predicts. Structure has formed a little more weakly, a little more slowly than expected. It is a smaller disagreement than the Hubble tension, and less certain, but it is there, and it points, like the Hubble tension, to something the model is not quite getting right. It is worth understanding how this clumpiness is even measured, because the method is one of the most ingenious in modern astronomy. When light from very distant galaxies travels toward us across billions of light years, it passes through all the intervening matter in the universe, and the gravity of that matter bends the light ever so slightly, distorting the shapes of the distant galaxies as seen from Earth. The effect on any single galaxy is far too small to notice. But by measuring the shapes of millions upon millions of galaxies and looking for subtle, coordinated distortions, astronomers can map out where the unseen matter lies, including the invisible dark matter and how strongly it has clumped together. It is a way of weighing the universe's structure using the bending of light itself. And when this enormous survey is carried out and compared to what the standard model predicts from the ancient light, the numbers come out slightly, persistently off. The real universe is a touch smoother, a touch less clumped than the model says it should be. Now, on its own, this clumpiness tension might not amount to much. It is at a lower level of significance than the Hubble tension, and there are various possible explanations, some of them mundane, but it does not sit on its own. It sits alongside the Hubble tension, pointing in its own way at the same uncomfortable conclusion that our model of how the universe evolves from its infancy to now is not capturing something real. There are stranger anomalies still in the ancient light itself. When cosmologists examine the great map of the cosmic microwave background, they find a handful of peculiar features that, by the standard model, should not really be there. There is an unusually large cold spot in one region of the sky, colder than the model easily explains. There is a strange alignment of certain large-scale features, an alignment that has been nicknamed, half in jest, the axis of evil, because there seems to be no good reason for the early universe to have a preferred direction like that. There is a subtle lopsidedness, a difference in the pattern of ripples between one half of the sky and the other. Each of these oddities is individually small, and each could perhaps be a fluke, but they persist. Better measurements have not made them go away, and there is an old, nagging problem with one of the lightest elements. Our theory of how the first atomic nuclei formed in the minutes after the Big Bang makes very precise predictions about how much of each light element should have been created. For most of them, hydrogen and helium, the predictions match the observations beautifully, one of the great triumphs of the theory. But for the element lithium, the prediction is off. The theory predicts substantially more primordial lithium than we actually find in the oldest stars. This lithium problem has stood unsolved for a long time. Another small, persistent crack This lithium problem is worth a closer look, because it is a genuine and long-standing embarrassment for an otherwise spectacularly successful theory. In the first few minutes after the Big Bang, while the universe was still hot and dense enough for nuclear reactions, the lightest elements were forged out of the primordial soup of particles. This process, the cooking of the first nuclei, is understood in remarkable detail, and its predictions for hydrogen and for the various forms of helium agree with what we observe to extraordinary precision. It is one of the strongest pillars of evidence for the Big Bang itself. But the same calculations predict a certain amount of lithium, and when astronomers measure the lithium in the atmospheres of the oldest stars, the stars that formed from nearly pristine primordial material, they find only about a third of what the theory says should be there. 2/3 of the predicted lithium is simply missing. Decades of work have failed to fully resolve the discrepancy. Perhaps the lithium is destroyed inside the old stars in some way we do not fully understand. Perhaps there is something wrong with the nuclear physics in our calculations. Or perhaps, like the other cracks, it is a hint of something deeper. Nobody yet knows. Now, any one of these, taken alone, might be explained away. A single anomaly is just an anomaly. But step back and look at them all together. A disagreement about the expansion rate at more than 5 sigma. A disagreement about the clumpiness of the universe. Strange features in the ancient light that will not go away. A persistent problem with primordial lithium. Several independent cracks, in several independent places, all in the same model. At some point, a collection of anomalies stops looking like a series of unlucky flukes and starts looking like a pattern. And a pattern of cracks suggests that the foundation, however magnificent the structure built upon it, may be incomplete. This is the uncomfortable position that modern cosmology finds itself in. The standard model of cosmology is, without exaggeration, one of the most successful scientific theories ever devised. It takes a handful of numbers and from them explains an astonishing sweep of observations, from the pattern of the ancient light to the distribution of galaxies across billions of light years. It is a triumph of the human mind, and it may also be incomplete. Both of these things can be true at once. The model can be extraordinarily successful and still be missing something fundamental, and the Hubble tension, along with its companion cracks, may be the universe's way of telling us so. So where does this leave us? It leaves us watching and measuring and waiting, because a disagreement this sharp cannot remain unresolved forever. Either we will find a flaw that closes the gap, or the gap will harden further into undeniable proof of new physics. And there is a whole new generation of instruments and observations now coming to bear on the question, any one of which might tip the balance. The powerful new space telescopes of our era are now observing those pulsing Cepheid stars at greater distances and with greater clarity than ever before, peering through the dust and the crowding that critics worried might be skewing the ladder's measurements. So far, rather than finding the hoped-for error, these sharper observations have largely confirmed the ladder's answer. They have not made the tension go away. If anything, they have made it harder to blame on a mistake in the ladder. New observatories are coming online that will discover thousands upon thousands of new exploding stars, the Type 1a supernovae that form the ladder's top rung, vastly increasing the data and tightening the local measurement further. Great new surveys are mapping the distribution of galaxies and the behavior of dark energy across cosmic time with unprecedented precision, watching closely for any sign that dark energy changes, that it is not the simple constant our model assumes. And there is one method that may eventually serve as a kind of tiebreaker, a completely independent way of measuring cosmic distances that climbs no ladder at all. When two extraordinarily dense objects, such as neutron stars, spiral into each other and collide, They send out ripples in the fabric of space itself, gravitational waves, which our instruments can now detect. And remarkably, the pattern of those waves encodes the distance to the collision directly, written into the physics of the waves themselves, with no need for any chain of calibration. These events have been called standard sirens, by analogy with the standard candles of light, and as we detect more and more of them, they may give us a measurement of the expansion rate that is independent of both the ladder and the ancient light. A third voice that could help settle which of the first two to believe, or tell us that the truth is stranger than either. The beauty of this method is worth appreciating because it sidesteps the entire structure we spent so long building. The distance ladder, for all its careful rungs, is ultimately a chain, and a chain can have a weak link anywhere along its length. Every rung depends on the one below it, and a subtle error at any level propagates upward. The standard sirens need no chain at all. The gravitational waves from a collision of neutron stars carry the distance to that collision encoded directly in their form, in the way the signal rises and fades, derived straight from the fundamental physics of how such waves are produced and how they travel. There is no calibration against nearer objects, no accumulation of small uncertainties up a ladder. It is, in a sense, a measurement from first principles. The first such measurement, from a single spectacular collision detected several years ago, gave a value for the expansion rate that sat tantalizingly right in the middle between the two warring numbers, with uncertainties too large to settle anything. But that was one event. As the detectors improve and more collisions are caught, the uncertainties will shrink, and this entirely independent third path may eventually speak clearly enough to tip the balance one way or the other. So the question is not closed. It is, if anything, more open and more actively pursued than ever. Somewhere in the data now being gathered, or in the data still to come, the answer may be waiting. A hidden error that will close the gap and restore the old picture, or a confirmation that will force us to rebuild it. Here is what we know. We measured the universe twice. The first measurement looked outward, across the cosmic distance ladder, climbing rung by rung from the geometry of nearby stars, through the pulsing Cepheids to the brilliant exploding stars in the deep universe. It looked at the cosmos around us, as it is now in the present day, and it gave us one number, 73. The second measurement looked backward, across nearly 14 billion years, into the oldest light in existence, the faint afterglow of the Big Bang itself. It read the pattern frozen into that ancient light and projected it forward through our best understanding of how the universe evolves. And it gave us another number, 67. The two numbers do not agree. And they disagree now at a level that scientists regard as proof, not of a mistake, but of something missing from our understanding. Something we have not yet found. The chance that it is mere coincidence has fallen below 1 in 3.5 million, and every new measurement, rather than closing the gap, has only sharpened it. For a century, the Hubble constant was the number we used to measure almost everything else about the cosmos. The age of the universe, the size of the observable cosmos, the scale of the heavens. It was the master ruler, the foundation on which a great edifice of knowledge was built. And that ruler may now be the thing that breaks, not because we measured carelessly, but because the universe, measured honestly by two different paths, has told us two different things. And if the ruler breaks, then some of what we built upon it will have to be examined again, and perhaps rebuilt. There is no need to find this frightening. It is, in truth, one of the most exciting moments a science can have. Every great leap forward in our understanding of the cosmos has begun exactly here, with a small, stubborn fact that refused to fit, a discrepancy that would not go away no matter how hard people wished it would. The old picture cracks, and through the crack, something new and deeper becomes visible. We may be living in exactly such a moment now, standing at the edge of a discovery whose shape we cannot yet make out. There is something almost beautiful in the situation when you sit with it. For all our instruments and all our mathematics, the universe has handed us a genuine mystery, the kind that cannot be waved away or argued out of existence. Two numbers, each measured with exquisite care, each refusing to yield. We tend to imagine that science slowly fills in the map, that the blank spaces shrink year by year until one day the whole picture is complete. But it does not really work that way. Every answer opens new questions. Every map, drawn carefully enough, reveals a new and stranger coastline at its edge. The Hubble tension is one of those new coastlines, a reminder that the universe is still, after all this time, larger and deeper and more surprising than our understanding of it. We thought we had measured the expansion of the cosmos. We had, and in measuring it well enough, we discovered that we do not understand the thing we measured. We do not know what comes next. We do not know whether the answer is early dark energy, or a dark energy that grows over time, or some new particle, or a subtle flaw in our theory of gravity, or something stranger than any of these that no one has yet imagined. We know only this. We have measured the one universe we live in twice with all the care and rigor we possess, and the universe has answered us in two different voices. And the gap between those voices is not closing. It is growing. Rest well.